Welcome to the Abundance Paradigm, our strategic outlook for 2026 to 2035. This analysis delves into the critical convergence of three transformative forces: infinite energy, orbital computing, and autonomous labor. Together, these elements are poised to reshape our economic and social landscapes in unprecedented ways. We stand at the precipice of what we call the Great Decoupling. This is a period where economic output is set to decouple dramatically from traditional human labor hours. By 2026, the technical foundations will be firmly in place for a zero marginal cost economy. The next decade won't be defined by invention, but by scaling what we already understand. The fundamental physics are largely solved. It's the economics that are now collapsing under the weight of these advancements. This paradigm shift is driven by three key pillars. First, infinite energy. Moving from terrestrial scarcity to solar abundance, leveraging an incredible 1,366 watts per square meter flux. Second, infinite compute, transitioning from grid-constrained data centers to innovative orbital data centers and highly efficient silicon, specifically AI-5. And third, infinite labor, evolving from human limitations to scalable autonomous agents, exemplified by Optimus robots and full self-driving technology. At the heart of this paradigm is a trillion-dollar closed-loop ecosystem comprising SpaceX, xAI, and Tesla. Consider this SpaceX, with an estimated IPO valuation potentially reaching $1.5 trillion, provides the critical infrastructure. xAI, with its intelligence platforms like Grok and Dojo, forms the brain. Tesla, with its millions of vehicles and advanced agents like Optimus, provides the physical manifestation and data collection. The loop is elegantly simple yet profoundly powerful. Robots build solar energy systems, solar powers rockets, rockets launch compute into orbit, and that compute then trains the next generation of robots. This continuous feedback loop accelerates innovation and drives exponential growth across all three entities. Let's dive into Pillar 1. The math of terrestrial abundance. Contrary to popular belief, land is not the bottleneck for solar energy. For instance, the total energy needs of the entire United States could be met by solar installations covering just 0.78% of the U.S. land area. A case study in Texas shows that generating 100 gigawatts of power would require approximately 700,000 acres, which is less than 0.5% of the state's land. The real constraint on terrestrial solar, however, lies in managing intermittency, which demands massive battery arbitrage solutions like megapacks to ensure a consistent power supply. This brings us to a more sustainable solution, escaping the atmosphere with space-based solar power. On Earth, solar flux is about 1,000 watts per square meter, and it's intermittent, available only during the day. In orbit, however, the solar flux is a significantly higher 1,866 watts per square meter, and critically, it's continuous, 247. Orbit offers constant production and superior radiative cooling. The advantages are clear: 40% higher solar flux than Earth, 247 uptime in a sun-synchronous orbit, and cooling facilitated by the near-absolute zero temperature of deep space. This power can then be transmitted back to Earth via microwave or laser to ground antennas. Moving to Pillar 2, the logistics of orbit. The economics of space access have been utterly transformed. Historically, the space shuttle had a launch cost of around $50,000 per kilogram to low Earth orbit. The Falcon 9 drastically reduced this to about $2,500 per kilogram, already enabling the deployment of 10-megawatt solar arrays per flight with its 150-ton payload capacity. But the true game-changer is Starship, projected to lower costs to an astonishing $100 to $200 per kilogram. At these price points, space no longer becomes just a destination. It becomes the lowest-cost environment for high-performance computing, unlocking entirely new possibilities. This leads us directly to the concept of the orbital data center, or ODC. Imagine 1 terabit per second bandwidth capacity, facilitated by optical laser interlinks forming a mesh network. The key insight here is that Starlink V3 isn't just a communications relay, it's designed as an edge computing node. The speed of light in a vacuum is significantly faster than in glass fiber, offering a fundamental advantage. Elon Musk himself has stated that simply scaling up Starlink V3 satellites would make this vision a reality. A prime application will be Starcatcher direct solar-to-compute transmission, bypassing terrestrial limitations entirely. Now, let's discuss silicon sovereignty, specifically the AI-5 chip and the terafab vision. Tesla's AI-5 chip is a powerhouse, offering H100 class inference performance with a remarkably low power draw of approximately 250 watts, compared to enterprise chips that consume over 700 watts. This is set to become the highest volume AI chip production globally, with an incredibly rapid 9-month design iteration cycle from AI-5 to AI-6 and AI-7. Tesla is strategically avoiding dependency on high-margin enterprise GPUs. The overarching terafab vision enables the mass production of these chips for both terrestrial robots and the orbital nodes we just discussed, ensuring vertical integration and control over a critical resource. This sophisticated hardware feeds into the intelligence loop, powered by xAI and Dojo. It begins with massive data collection. 7 million Tesla vehicles constantly gather video data from real-world driving. This data is then fed into training. The Colossus cluster, comprising 100,000 GPUs alongside the upcoming space-based Dojo 3, processes this information. A significant advantage here is simulation. Training models can generate photorealistic simulations, drastically reducing the need for physical FSD test miles by an impressive 90%. This refined intelligence is then deployed, leading to improved FSD and Optimus models, which in turn gather more data, perpetuating the loop and accelerating development. Pillar 3 focuses on the physical agent, specifically Optimus Gen 3. This humanoid robot boasts 22 degrees of freedom, including a highly articulated wrist and forearm with 3 degrees of freedom. It features a 40% battery efficiency improvement, enabling a walking speed of 6 to 7 miles per hour. Its custom linear actuators, utilizing planetary roller screws, contribute to its precision and strength. Crucially, the economics are game-changing. The targeted production cost for Optimus is between $20,000 and $30,000, making it less expensive than a standard car, and therefore a highly accessible labor solution. Let's look at the roadmap to ubiquity for Optimus, spanning 2026 to 2035. Phase 1 from 2026 to 2027 focuses on internal industrial deployment within Tesla factories, handling hazardous and repetitive tasks. Phase 2, from 2028 to 2030, scales commercially, moving into B2B sales and partnering with manufacturing and logistics companies. Finally, Phase 3, from 2030 to 2035, sees domestic integration, with consumer availability for home assistance and elder care. The ultimate golden goose scenario is when Optimus gains the capability to manufacture more Optimus units, at which point the marginal cost of labor truly trends toward zero, unleashing unprecedented productivity. In autonomous mobility, we are entering the cybercab era. Tesla FSD operates on a vision-only architecture. This camera-centric approach allows it to scale globally without reliance on high-definition maps, a significant advantage. The cybercab vehicle, designed without a steering wheel or pedals, targets an incredibly low operating cost of just $0.20 to $0.30 per mile. In contrast, competitors relying on sensor fusion LiDAR, radar, and maps often face higher complexity, requiring geofencing and hardware-heavy solutions. Current costs for services like Waymo hover around $0.60 to $0.80 per mile. The technical completion of unsupervised FSD is anticipated by 2026, marking a pivotal moment in this transition. These advancements collectively lead to the economics of abundance. We anticipate a massive cost collapse, as energy from solar and labor from Optimus drive down the prices of goods and services. This deflationary event is profound. As a result, we could see a shift towards universal high income, not merely as survival payments, but as a pathway to luxury abundance. Furthermore, energy itself will likely replace fiat currency as the dominant store of value. The overall productivity and automation capacity will surge, leading to what we define as the deflationary event, a fundamental reshaping of economic value. This brings us to the societal horizon, a post-work world. Imagine decentralized living, where residency is decoupled from traditional job centers. Architecture will shift from efficiency-centric office towers to vibrant creative community hubs, incorporating solar roofing, green spaces, vertical farms, and community workshops. High-speed satellite links like Starlink dishes will be ubiquitous. The most profound shift, however, will be the Great Filter, redefining human purpose when it is no longer tied to productivity. This future envisions adaptable residential modules and an emphasis on communal and experiential living. Finally, let's consider the investment horizon for 2026. The major catalyst here is the potential SpaceX IPO, which could inject a massive $1.5 trillion, funding the next phase of orbital infrastructure development. This investment will accelerate the build-out of a powerful stack at the base, infinite energy through photovoltaic integration, renewable sources, and a march towards zero marginal cost energy. Next, orbital compute via Starlink and orbital data centers, providing global connectivity, edge computing, and low latency. And at the top, autonomous labor, embodied by Optimus as a multi-purpose humanoid, AI-driven, scalable workforce. This convergence promises a future where truly, if you can think it, you can have it.